In today's video, we're going to look at the terms activity and half-life, and see how we can calculate each of them. We've already seen that some materials contain unstable isotopes, and that in order to become more stable, they can decay by emitting some form of radiation, like an alpha particle, a beta particle, or gamma rays. We call materials like this radioactive, and they come in loads of different forms. If we were to consider a single radioactive isotope, we'd have absolutely no way of knowing when it would decay, because the decay process is completely random. However, if we have a large enough sample of radioactive isotopes, then even though we couldn't tell when any individual isotope would decay, we can still find out two very useful things. One is the activity of the sample, which is the overall rate of decay of all the isotopes in our sample. And we measure activity in becquerels, where 1 becquerel represents 1 decay per second. So if a sample had an activity of 600 becquerels, then there must be 600 isotopes decaying each second in that sample. The other important term to know is half-life, which has two definitions, and can be defined either as the time taken for the number of radioactive nuclei in a sample to halve, for example to drop from 1,000,000 unstable nuclei to only 500,000, or the time taken for the number of decays, so the activity, to halve, for example to drop from 600 decays per second to 300 decays per second. To properly understand these concepts, let's imagine our radioactive sample as 100 unstable isotopes, each of which can decay by emitting radiation in order to become stable. So if we watch this sample decay, the first thing we notice is that the decay process is completely random. So we have no way of knowing when any particular particle will decay. As time goes on though, and more of them decay, the number of unstable particles remaining decreases. Because there are fewer particles left to decay, this means that the overall rate of decay, which remember is the activity, will also decrease. Which is why it looks like the sample is decaying more slowly than it was at the start. This is why we can define half-life as a halving of either the number of radioactive nuclei remaining, or a halving of the activity. They are both perfectly correlated, because fewer radioactive nuclei means a lower activity. Another way to show this decay process is by using a graph that plots activity in becquerels against time. As time goes on, the number of particles remaining and the activity of the sample will decline. But the rate of decline will also fall, which is why it's curved rather than a straight line. To calculate the half-life from a graph like this, we need to find the time it takes for the activity to halve. So in this case, drop from 600 to 300, which we can see is about 2 hours. And to confirm this, we could check another one by seeing how long it takes it to halve again down to 150. And indeed, it does take another 2 hours, so we can be confident that the half-life is 2 hours. If we had a different radioactive sample though, like this one, we can see that it's decaying much more quickly. This means that it started with a much higher activity, as we can see on our graph, and also that it will decline much more rapidly, and so a much shorter half-life, this time of 1 hour. Now, so far, we've just kind of assumed that we'd know what the activity is. In real life, though, we'd have to find the activity using a device called a Geiger-Müller tube encounter. These things record all the decays that reach them each second. So all of those alpha and beta particles and gamma rays, which it then records as the count rate. and it's this count rate that we use to estimate the activity. Before we finish, let's try one quick question. The half-life of a radioactive source is 40 hours. There are initially 3 million radioactive nuclei in the sample. How many nuclei will remain after 5 days? In a question like this, the idea is to first find out how many half-lives there will be, and then half the number of radioactive nuclei that many times. So first, we need to take 5 days and times it by 24 hours to get 120 hours. And we can then divide that by 40, which is the source's half-life, to find out that the sample will have undergone 3 half-lives. So then we just take our 3 million radioactive nuclei and half them 3 times to get 1.5 million, 750,000, and finally 375,000, which would be our final answer. That's all for this video, so hope you enjoyed it, and I'll see you soon.